Hello and welcome to the Planetary Spectrum Generator video tutorials. I'm Sara Faggi, member of the PSG team, and with this video I will present the surface scattering modeling capabilities of PSG. For more information you can refer to chapter 6 of the PSG Handbook. As light at a particular wavelength arrives to a surface, it can be either absorbed or scattered, reflected. A quantity that captures how much light is being reflected towards the observer is called bidirectional reflectance, which can be modeled employing different methods. In PSG, 5 core models are available: the Lambert or isotopic scattering model, the Hapke model, a parametric surface scattering model, the Longman model applicable to weakly scattering and diffuse surfaces, the CoxMook Model applicable to specular glimpse ocean scattering, and finally the Comet dust grains modeling. First, let us comment on the most commonly used surface model, the Lambert diffuse model. In a Lambert surface, fluxes are scattered isotropically as an ideal matter, or perfectly diffuse reflecting surface, while emissivity is defined as 1 minus albedo. In this model, the scattered intensity is only dependent on the incident angle. A parametric surface model is the Hapke scattering model, which is physically motivated model that provides an approximate solution for radiative transfer for a porous, irregular, and particulate surface. In PSG, we implement the generic Hapke isotropic multiple scattering approximation, ISMA model, which is useful if the surface scattering function is not too anisotropic and can be mostly described by a single scattering term. The implemented model can be adapted to employ several phase functions and includes both Hapke shadow hiding opposition effect, the Shoe factor, and the coherent backscattering opposition effect, CBOE, and a compensation for surface roughness. Several examples of parameterization for this model are presented in chapter 6. For relatively dark objects with weakly scattering surfaces, the Longman model performs well in capturing the variation of scattered fluxes with respect to the source observational angles. It is therefore the preferred model when interpreting the Moon, for example, asteroid, or other small bodies. Phase functions commonly used for this model can be chosen, including those for resolved surfaces, for example when modeling the Moon, or for unresolved measurements, for example when modeling asteroids or comets. If you are interested in modeling large bodies of water, a specific strong reflection occurs at certain phases, and in PSG, the ocean glimpse is modeled by employing the CoxMook model. The model employs geometric optics model with the assumption of a Gaussian distribution for the slopes of the wave facet. Specifically, Cox and Mook found that the probability density of function of the wave slope depends on the wind speed, and the probability determining glint reflection can be approximated by a Gaussian function. Let's now check in the last model, the cometary model. In the case of comet, dust and icy particles in the coma are in many cases the main source of the continuum broad radiation. Small particles have a very different response if compared to a solid body, with a strong forward scattering peak and a less shallow scattering phase function. In PSG, we employ a Lambert model with the Halley-Markus integral phase function compiled by Schleicher and Baer to model the scattering properties for the dust grain, independently of the selected nucleus scattering phase model. The intensity of the continuum would then depend on the effective emitting area of the dust grain, and for that we employ a model as described in Villanueva et al. 2018. The user can use this model and the FRO method to determine the continuum intensity. Beyond selecting the model, the user can create a surface as a combination of several constituents, each with different scattering properties. In PSG, mixing of components is done via the areal mixture principle. In the areal mixture, the surface area viewed by the detector consists of several unresolved smaller patches, each of which consists of a pure material. In this case, the total reflectance is simply the linear sum of each reflectance weighted by area. A key parameter in surface modeling is the single scattering albedo. This parameter can be calculated for a specific surface from the optical constant, or it can be determined from a laboratory measurement of reflectance of that component, or it can be also derived from astronomical measurement. Scattering albedo, geometrical albedo, bond albedo, reflectance, absorptivity are all related quantities, yet they have very different meaning and their values can differ greatly from the same component. In PSG, the user can select from a selection of 30,000 spectroscopic sources. These have been integrated from 11 widely used planetary spectral repositories, including the USGS, the ReLab, and the Grenoble ICE databases. Hopefully, you have found this short video instructive. We encourage you to explore the handbook in detail and also to check other learning videos and online material. Ad astra and thank you.